Welcome to Chapter 3 of the Chiral Phonons series. In this chapter, we'll explore the experimental techniques used to detect and characterize chiral phonons. We'll cover circularly polarized Raman spectroscopy, circular dichroism measurements, helicity-resolved photoluminescence, and ultra-fast pump probe spectroscopy. These methods have transformed chiral phonons from a theoretical prediction to an experimentally observable phenomenon. By the end of this chapter, you'll understand experimental setups for circularly polarized Raman spectroscopy, Raman selection rules for chiral phonons, circular dichroism in phonon absorption, helicity-resolved photoluminescence for detecting valley polarization, ultra-fast spectroscopy techniques for time-resolved detection, and key experimental results in WSE2 and alpha quartz that confirmed theoretical predictions. Let's start with the fundamentals of Raman scattering. Raman scattering is an inelastic light scattering process where incident photons interact with phonons in a material. The scattered light frequency is shifted by the phonon energy. Omega scattered equals omega incident plus or minus omega phonon. For chiral phonon detection, the key innovation is using circularly polarized light to probe phonon angular momentum. In circularly polarized Raman spectroscopy, we distinguish between two configurations. Copolarized means incident and scattered light have the same circular polarization, either sigma plus/sigma plus or sigma minus/sigma minus. This selects phonons with zero angular momentum projection, like A1 modes. Cross-polarized uses opposite polarizations and selects phonons with angular momentum m equals plus or minus 1, which are the chiral E' modes we're interested in. Here's the experimental setup for circularly polarized Raman spectroscopy. A laser source produces linearly polarized light. A quarter wave plate oriented at 45 degrees converts this to circular polarization, either sigma plus or sigma minus, depending on the fast axis orientation. The circularly polarized light hits the sample, and scattered light passes through an analyzer system consisting of another quarter wave plate and linear polarizer. Finally, the signal reaches the spectrometer and CCD detector. The quarter wave plate is the key optical element. It converts linear polarization to circular by introducing a 90-degree phase shift between orthogonal components. The fast and slow axes of the waveplate create this differential phase delay. By rotating the input linear polarization, or the waveplate, we can generate either sigma plus or sigma minus circular polarization. Precise alignment is critical for accurate measurements. Raman scattering intensity is determined by the Raman tensor R and the polarization vectors of incident and scattered light. The intensity is proportional to the squared magnitude of es.r.ei for chiral phonons with angular momentum m. The Raman tensor has specific symmetry properties. In monolayer TMDs with D3H point group, the E' mode splits into left-handed and right-handed components, each with distinct Raman tensors. Here are the selection rules for different phonon modes. The A1' breathing mode has zero angular momentum and is active in copolarized configurations. The E'(R) right-handed mode with m equals +1 is active in sigma plus/sigma minus configuration at the K valley. The E'(L) left-handed mode with m equals -1 is active in sigma minus/sigma plus at the K' valley. These valley-dependent selection rules are the experimental signature of chiral phonons. Several experimental factors require careful attention. Valley selection means that chiral phonon selection is valley-dependent due to valley-phonon coupling. Sample quality is important because defects and strain can break selection rules and cause depolarization. Detection efficiency depends on quarter wave plate alignment and optical aberrations. Temperature effects can cause phonon line width broadening and affect the measured polarization degree. The circular polarization degree PC quantifies the chiral nature of phonon modes. It's defined as the difference of copolarized and cross-polarized intensities divided by their sum. When PC equals +1, the mode is purely copolarized and non-chiral, like the A1' mode. When PC equals -1, it's purely cross-polarized and strongly chiral. Values between these extremes indicate mixed character or experimental imperfections. Now let's move to circular dichroism in phonon absorption. Infrared circular dichroism provides another method to detect phonon chirality by measuring differential absorption of left and right circularly polarized infrared light. Circular dichroism is the differential absorption of left and right circularly polarized light. The CD signal is defined as the absorbance for sigma plus minus the absorbance for sigma minus. For phonons, RCD arises when phonon modes carry angular momentum. The sign of the CD signal indicates the handedness of the phonon mode. Phonon circular dichroism requires two conditions. First, broken inversion symmetry, which allows phonon angular momentum. Second, phonon-light coupling through either electric dipole or magnetic dipole transitions. The CD signal is related to the rotational strength R, which is the imaginary part of the dot product of the electric dipole moment mu and the magnetic dipole moment m in chiral crystals like alpha quartz. The helical crystal structure enhances phonon-photon coupling. Next, let's discuss helicity-resolved photoluminescence, another powerful technique for probing chiral phonons through their coupling to vary degrees of freedom in 2D materials. In monolayer TMDs, optical transitions at K and K' valleys couple to circularly polarized light with opposite helicities. Starting with sigma plus excitation, we create K valley excitons. During relaxation, these excitons can emit chiral phonons. The relaxed excitons then recombine, emitting sigma plus polarized photoluminescence. Similarly, sigma minus excitation creates K' valley excitons that emit opposite chirality phonons and produce sigma minus PL. Valley polarization PV is defined as the difference of sigma plus and sigma minus photoluminescence intensities divided by their sum. A high PV value indicates strong valley polarization maintained throughout the optical process. The valley polarization is directly linked to the chiral phonon modes involved in exciton relaxation, making helicity-resolved PL a probe of valley phonon coupling. Chiral phonons play crucial roles in several phonon-assisted processes. First, phonon replicas appear as sidebands in PL spectra, separated by phonon energy, and show valley selectivity. Second, valley depolarization occurs through intervalley scattering mediated by specific phonons. Third, indirect transitions in momentum-indirect materials require phonon assistance for absorption and emission. Each process reveals information about phonon chirality. Now let's explore ultra-fast spectroscopy, which enables direct observation of chiral phonon dynamics with femtosecond time resolution. Ultrafast pump probe spectroscopy uses a pump pulse to excite the material and a probe pulse to detect transient changes in optical properties as a function of time delay. The pump can be circularly polarized for valley selective excitation. The differential transmission reveals coherent phonon oscillations. Delta t over t equals amplitude times cosine of omega ph times t plus phase, multiplied by an exponential decay with time constant tau. This directly measures phonon frequency and dephasing time. Coherent phonons are generated through several mechanisms. Displacive excitation, or DECP, creates a sudden change in equilibrium lattice position, producing symmetric A1 modes. Impulsive stimulated Raman scattering, or ISRS, is a coherent Raman process with ultra-short pulses that can generate chiral phonons when using circularly polarized pump. Valley selective excitation uses a circularly polarized pump to create valley polarization, which through valley phonon coupling drives chiral phonon oscillations. Different pump probe polarization configurations detect different phonon types. Co-circular, sigma plus pump and sigma plus probe detects non-chiral modes plus valley-specific contributions. Countercircular, sigma plus pump with sigma minus probe, selectively detects chiral phonons. Cross-linear configuration with perpendicular linear polarizations detects all Raman active modes. By comparing these configurations, we can isolate chiral phonon signatures. While optical spectroscopy probes zone-center phonons, inelastic neutron and X-ray scattering can measure phonon dispersion throughout the Brillouin zone. Polarized neutron scattering is interesting because neutrons carry spin, allowing spin-phonon coupling measurements. Challenges include neutron flux limitations requiring large samples and the difficulty of separating chiral signatures. Opportunities include complete dispersion mapping, momentum-resolved angular momentum, and magnon-phonon coupling in magnetic materials. Let's now examine the key experimental results that confirmed chiral phonon predictions. We'll focus on landmark experiments in monolayer WSE2 and bulk alpha quartz. The landmark experimental observation of chiral phonons was reported by Zhu and colleagues in 2018 in Science. They studied both monolayer WSE2 and bulk alpha quartz. Key findings include circular polarization of the E' mode at about 250 wave numbers, valley-dependent selection rules where different circular polarizations couple to different valleys, high circular polarization degree for chiral modes, persistence of chiral signatures up to room temperature, and stronger chirality in monolayer compared to bilayer due to interlayer coupling. This work provided the first definitive experimental confirmation of the 2015 theoretical predictions by Zhang and Niu. The experimental configuration used a 532 nanometer green laser resonant with exciton transitions. Samples were mechanically exfoliated monolayer WSE on silicon dioxide on silicon substrates. Measurements covered temperatures from 10 Kelvin to 300 Kelvin using a backscattering geometry with a confocal microscope for spatial resolution on the micrometer scale flakes. Zhu and colleagues in 2018 demonstrated chiral phonons in the 3D chiral crystal alpha quartz. They observed strong phonon circular dichroism in infrared absorption at around 400 and 800 wave numbers. Crucially, the CD sign reversed between left-handed and right-handed quartz crystals, confirming the structural origin of phonon chirality. Raman spectroscopy showed polarization-dependent intensity, and calculated phonon angular momentum agreed with experimental CD spectra. The alpha quartz results had significant implications. They demonstrated that chiral phonons exist in 3D bulk crystals, not just 2D materials. This established that any crystal structure lacking inversion symmetry with appropriate symmetry breaking can support chiral phonons. The comparison between 2D TMD monolayers and 3D quartz showed that phonon chirality is a general phenomenon across different material dimensionalities. Let's discuss Python simulations for Raman polarization dependence. We'll implement Raman tensor calculations, circular polarization vector definitions, and intensity calculations using NumPy and Matplotlib. These simulations help understand the polarization-dependent selection rules we discussed earlier. The implementation uses two key Raman tensor functions. For the A1 non-chiral mode, the tensor is diagonal, representing isotropic in-plane response. For E' chiral modes, the tensor is off-diagonal with a chirality parameter of plus or minus 1. The circular polarization vectors are defined as E plus equals x hat plus I y hat over root 2 for sigma plus and E minus for sigma minus. Raman intensity is calculated as the squared magnitude of the matrix element. The simulation produces clear predictions. For the A1 prime mode, we expect strong copolarized signal with PC equals plus 1 and 0 cross-polarized intensity. For the E' right chiral mode, sigma plus slash sigma minus gives strong cross-polarized signal, while sigma minus slash sigma plus is 0. The left chiral mode shows the opposite pattern. These predictions match experimental observations beautifully. We can also simulate phonon circular dichroism spectra. Using Lorentzian line shapes for absorption, we model the CD signal as having dispersive character due to the relationship between absorption and CD. For alpha quartz, we include multiple modes at different frequencies with positive or negative chirality. The total CD spectrum shows sign-changing features at each mode frequency, matching experimental observations. For coherent phonon dynamics, we simulate the pump probe signal as damped cosine oscillations, including multiple modes like the E' at 7.5 terahertz and A1' at 8.2 terahertz produces a beating pattern. Fourier transform of the time domain signal reveals peaks at the phonon frequencies, allowing extraction of both frequency and dephasing time from experimental data. Let's summarize Chapter 3. We covered circularly polarized Raman spectroscopy with valley-dependent selection rules. Infrared circular dichroism directly probes phonon angular momentum. Helicity-resolved photoluminescence reveals valley-phonon coupling in 2D materials. Ultra-fast pump probe spectroscopy captures coherent chiral phonon dynamics. And landmark experiments in WSE2 and alpha quartz confirmed theoretical predictions and established experimental protocols. In Chapter 4, we'll explore applications and computational methods for chiral phonons. Topics include DFT calculations using Phonopy and Quantum Express to calculate phonon angular momentum transport phenomena, Valatronics applications for information processing, and emerging device concepts like phonon transistors and polarizers. See you in the final chapter.